All right, well, it's a little strange to be addressing you on Zoom from New York. I'll be back in California shortly. Because it's a little difficult to run a meeting on Zoom from here while you're all there. Greg has kindly agreed to introduce our speaker. I'll just make a few announcements beforehand, and then if other people have announcements, we'll do those as well. So I just wanted to remind people that our annual dinner meeting in May is going to be May 31st, the last Wednesday in May. It's a little later than we've had it in the past, and you should be receiving a registration form end of this week. So we're just finalizing the arrangements with the barbecue place, and then we'll go ahead and send out the registration. So are there any announcements from either people online or in the room? Yeah. Let's start within the room.
Gary Prost. Just for your information, the El Cerrito Hillside Festival is going to be on Saturday, May 6th. And Bill Motzer and Mark Petrovsky and I are going to be leading a geology walk at noon, be about 2 to 3 hours. And it's essentially the same as the field trip that we did for NCGS a year or so ago. So if anybody's interested, everybody's welcome. There's no cost.
Where is this? I guess the first time
It's going to be on Schmidt Lane at the recycling center in El Cerrito. We're going to start.
Thank you. Any other announcements? All right, it's a small group tonight. Less chatty than usual. Greg, do you want to take it from here?
Hi, I'm Greg Bartow, and I'm going to introduce Larry in a minute, but also just Andrew Alden just came in, and he will be our speaker in June, speaking about his new book, Deep Oakland, How Geology Shaped the City. And so this is just out on, is it Heyday? Heyday Press. So, you know, an exciting new book from one of our members and board members. And so noteworthy about the book's availability, and also he will be our June speaker. Then Larry Toy is he received his bachelor's degree from Harvard and his master's and PhD from UC Berkeley, all in astronomy. He spent much of his career teaching astronomy at Chabot College and was honored as one of the first 4 outstanding faculty selected from 15,000 faculty of the California community colleges. He is a founding board member of the Chabot Space and Science Center. And for the final decade of his career, Larry served as the president and CEO of the Foundation of California Community Colleges. He also served on the California Council of Science and Technology. Larry, thank you very much for being the speaker, and I'll turn it over to you.
Thank you very much, Gary, and thanks and hello to everyone. I know that our former neighbor in Orinda, Steph Curry, is doing something tonight, so hope he's successful. I'm going to share my screen and talk a little bit about the Webb telescope, and also give you a little history lesson. I'm old enough that I can do that, and share with you a little bit of how astronomy developed. Let me get my screen ready to share. Okay, and I hope you can see that. Can everyone see that slide? I hope you can see that. Thank you. This is a drawing of the Space Telescope, because we don't have cameras out there, can take pictures like this. And I'll talk a little bit about the telescope itself and then some of the more recent discoveries that have been made. It's actually a very new telescope in a way, but also a very old one. First of all, who is James Webb? This is James Webb, picture of him. And he was the NASA administrator from 1961 to 1968. And his claim to fame primarily was he was appointed by John Kennedy. And during the first few months of Kennedy's administration, James Webb, Lyndon Johnson, and Kennedy got together, and Kennedy said, is there any way we can get the moon soon? And that started the Apollo project, and Webb was the administrator in charge of the Apollo project, and he was there until the end of Johnson's administration in '68, and oversaw the first few launches of the Apollo up through, I think, Apollo 11 or Apollo 12, and then Apollo 10, and then Apollo 11 landed in 1969. So that's James Webb. He was not a scientist. He was actually a politico. So he started his first job working as an assistant to one of the congressmen, but he worked his way up and became a very competent administrator. Well, the Webb telescope is an interesting telescope. I'll talk to you more about that, but it was launched just about a year and a half ago. It was launched using the Ariane 5 rocket from the European Space Agency, because we didn't have a capability of sending up such a big instrument at that time. And we're starting to develop more capability now with primarily with the SpaceX rocket. And that will be taking the next return to the moon project, which is coming up in the next couple of years. This was from French Guiana on Christmas Day of 2021. And what I like to point out to you is the width of this instrument. And I hope I'm not sure, can you see my arrow there? Yes. Going across my cursor? Yes. That width of that arrow of the telescope, of the rocket, is actually narrower than the width of the instrument. And there's the instrument again a drawing. In fact, it's narrower than this, the mirror itself, which is, by the way, a segmented mirror that you can see, and I'll talk a little bit more about that. So how do they do it? This is an origami, essentially. What they did is they folded up the whole telescope so that it would fit inside the nose cone. It's an amazing project. On the right is a drawing of it, but on the left is the real thing. This is the fitting into the nose cone of the rocket. And the trick here, of course, is there's nobody there along with the rocket. So as it goes into space, if it doesn't unfold properly, you're stuck. So it's one of the problems that astronomers have, is that if you're using telescopes out in space, it's hard to repair them. And it's hard to fix it if it gets stuck. But fortunately, it didn't get stuck. And I'll show you a bit of the path. It's sort of an amazing instrument that way. Although it was launched just about a year and a half ago, the first ideas of it came about the same time the Hubble was being finalized. And so they thought, well, let's have another telescope after Hubble. And so they started thinking about it, and about 25 years ago was when the go-ahead came for developing the Webb Space Telescope. Well, here you see the path of the telescope, and I'll show you some things. Of course, this is not to scale at all, but this is the Earth here the launch took place again in French Guiana. And here's an orbit of the moon. And you can see the various parts of it. There's a solar array, communications, sun shield deployment. That's very important. The secondary mirror deployment. And finally, the primary mirror deployment. And then it led to a little interesting orbit called L2, which I'll get to in a second. But you notice another thing about it is that it's much, much farther than the orbit of the moon. And if you know, the moon is about 250,000 miles away from the Earth. And so this is about 1 million miles away from the Earth. So the Webb telescope is significantly farther away from the Earth than the moon. It's at a stable point in the sun-Earth orbit, and there's a scale of where the moon is, and here's where the Webb telescope is. It's called the Lagrangian point 2. I don't know whether geologists study Lagrangian points, but these are stable points in the relative orbit of 3 bodies. There's a famous problem in physics, it's just called the 3-body problem, and this is not solvable for stable orbits, except that you can have, with some assumptions, a stable orbit calculation based on a restricted 3-body problem, which means one of the bodies is particularly small, and that is, it happens to be the telescope here. And this position is a very interesting one, because it means, because of the pull of the gravity of both the sun and the Earth, that the position out here, even though it's farther away from the Earth, farther away from the sun than the Earth, this actually means that normally, according to standard 2-body problem gravitational calculations, this should be going around the sun more slowly than the Earth, okay, because it's farther away, less gravity, so forth. But because of the additional pull of the Earth's gravity on the object, it actually, this position actually moves at the same orbital speed as the Earth, which means the Sun-Earth telescope stay in this exact line as the Earth goes around the sun. The telescope is going around essentially always in the shadow or the direction of the shadow of the Earth. And that turns out to be extremely important. There are other stable points, L1, L4, L5, L3, but we won't worry about those. L2 is the most important one here. Okay, I'll tell you a little bit about gravity and how it works here. This is just a picture of a bowl, and normally you can get a stable position if it's like you have a gravity well. And if you think about it, taking a small ball and rolling it down into the bowl, it will roll back and forth and eventually settle at the bottom of the bowl. And if you push the ball slightly in any direction, what happens to the ball? I think you'll know it rolls back toward the middle, and that's a stable position. Now, the L2 position is a partially stable position, and it works more like a saddle. And this is the shape of a saddle. It rides, you can sit there right on the saddle, and the front of the saddle and the back of the saddle and the sides of the saddle. And you notice if you push the ball, which is sitting right in the middle point of the saddle, if you push it up the saddle, it'll roll back down stably. If it pushes it the other way, it'll roll back down. But if you push it to the left or the right, it's not stable and it'll come off. Well, it turns out that the Webb telescope is in this L2 position, which is a saddle shape. It is not quite at the top of the saddle. It's slightly facing the Earth, which means if we did nothing to it, it would roll down toward the Earth. Instead, there's a little booster rocket, and the little booster rocket is constantly pushing the Webb telescope slightly upward toward that central saddle position, but not too much. So it doesn't actually reach there. So what happens is this is a quasi-stable position. As long as you have enough fuel in the tank to keep it in this position, this Webb telescope will stay for a very long time. Initially, there was enough fuel projected out that it would take about 10 years before it ran out of fuel. But because the deployments were just about perfect and they had to use less fuel than necessary, it turns out that the Webb telescope will be able to be kept up here for between 20 and 30 years. So it has a much longer lifetime than we had originally projected. If that makes sense. Okay. Now, the Webb telescope is a special kind of telescope. It's an infrared telescope. And those of you who know about infrared, if you take your hand and place it very close to your face, but don't touch it. Okay, if you can do that, take your hand and put it very close to your face. You can feel the heat of infrared energy from your hand without touching. You can try this with a friend, but don't touch. And this is the energy that's coming out because your hand is at about 70 degrees Fahrenheit or plus 30 or so, whatever, plus 25 or so Celsius, maybe closer to 30 degrees Celsius. Well, if you are looking for infrared energy from space, then you need to keep the telescope side, which is this side, very cold. In fact, it is at about minus 233 Celsius or minus 388 Fahrenheit, not absolute zero, but still very, very cold. And all the scientific instruments are on this side. And the reason is, if there's a hot part of the telescope, then this infrared mirror would detect the energy from that hot spot. So this all is extremely well insulated. On the hot side, which faces the sun and the earth, it's much hotter, 185 degrees Fahrenheit or 85 Celsius, not quite to the boiling point of water. And on that side is a solar panel, which gives it energy, and also the communication satellite, the communication antenna, which sends the signal back to the Earth. And there's also a computer on this side. And then these very important reaction wheels and jets, which is what keeps the telescope in the right place. Okay. Now here's a picture of our galaxy, the Milky Way. Our Milky Way galaxy is called a barred spiral. The central spiral area, the central nucleus of the galaxy looks like a bar. And then there are spiral arms coming off of there. And if you can see very in small print, here's the picture of where we are, the sun. I hope you can see that. And to this scale, the whole solar system would be an incredibly small dot right in the middle of that. And then there are the stars. Some of you recognize some of these constellations because they like Orion and Perseus and some of the other ones, Sagittarius. These are the constellations that you see in the sky. They are all the stars that we see in the sky basically are within this little circle. but these are the directions that you see. So there's the Milky Way. Most of the stars here are well beyond what you can see without a telescope. Okay. So now, what do we see with the James Webb Telescope? Here's two pictures. This is a picture taken by the Hubble telescope. And this is a picture of the same area taken with the James Webb telescope. And the Hubble telescope takes pictures and collects data basically in the visible part of the spectrum. The James Webb telescope gets all of its information in the near infrared to mid infrared parts of the spectrum. Now, as you know, infrared energy is not visible to us. That means if you take your hand, you can feel the energy, but if you turned off the lights, you wouldn't be able to see your hand because the infrared energy is not visible to your eye. So all the colors that you see on the right side are fake colors. They're colors that allow us to see the differences, but those are all in the infrared part of the spectrum. Now, what the advantage of being in the infrared penetrates dust very well and gas very well. So you can see, for example, these two very bright stars, and here you can see they're actually buried in dust, and you can barely see them in the Hubble telescope view. Okay. It's quite a spectacular difference, and also because the James Webb telescope is much, much larger. It's 17 feet across. By the way, I think the width of the Ariane spacecraft was 14 feet across. So this is bigger than the Ariane nose cap. You can see the tremendous detail from this bigger mirror, and also because the light from these stars, which you can really not see at all almost in here, all these stars, barely see maybe a few. Can you see a couple up here and over here? Well, over here they're much, much brighter. They're penetrating all this gas and dust, which are in the Hubble picture, and you can see right through that in the James Webb telescope. Well, you know all about this, so I'm not going to spend much time on it, but the visible part of the spectrum where we see is very narrow, and we're talking about the James Webb telescope working in this area in the infrared. They have a near infrared telescope, which is just beyond the visible spectrum, and then a mid infrared telescope, which is out here somewhere. Okay. And we have now sent telescopes up which observe in all these different parts of the spectrum. So of course we have radio telescopes which are on the Earth, and then also microwave telescopes that operate in the microwave region. But we have ultraviolet telescopes that have gone up in satellites, X-ray telescopes, even gamma ray telescopes. Now there are two kinds of cameras, and this is a picture of one of the areas of star formation in the Milky Way galaxy. It's called the Tarantula Nebula. This is the near infrared camera, and you can see what it observes. And here you can see actually a star cluster here behind. You can see all these stars here. In the medium infrared, it's looking at quite a different view, but of exactly the same region. And again, you're seeing detail of dust and gas that you don't see in the near infrared. And the near infrared, you can see more of these stars, which put out its energy closer to the visible part of the spectrum, and therefore they're easier to see. You can see this very bright star here. You can see that here, but you can almost not see a few stars here, but not too many. Okay. We've also used the telescope to observe into the near area of planets. This happens to be Our biggest planet, Jupiter, which is about a little bit more than, I think, about 12 times the diameter of the Earth. And here's the famous red spot, because this is in a false color taken in the infrared. The red spot doesn't look very red. But if you look very carefully at the top and the bottom, these are aurora. So if we were sitting underneath here, we would see tremendous auroras in Jupiter. Of course, it'd be a little cold for us to be there, colder than Alaska. So if some of you have been up north during the wintertime and seen the aurora borealis, or the southern hemisphere has the same exact auroras going on in the southern area of the Earth. Here's another picture. This is a neat one. This is of Neptune. By the way, when I was growing up and starting to study astronomy when I was a kid, we knew that Saturn had rings, and now we know that Jupiter has rings, Uranus has rings, Neptune has rings. So all the four major big planets going around the sun all have rings. And here are the rings of Neptune, and here. And these are some of the moons of Neptune. When I was growing up, there were 2 known moons, but now we have, I don't know, 10 or 20 moons of Neptune and 30, 40, 50 moons of Jupiter. There's Triton, which is a big moon. This is an interesting moon. It's about this big as our moon, maybe a little bit bigger, and it goes in the opposite direction of almost all the other moons in the solar system. And we believe because of that, the Triton was actually a small planetoid that was captured by the gravity of Neptune and is going around Neptune as a captured moon. It was not one of the original moons that was going around Neptune. Again, you can see some of the spots on Neptune here, and maybe it's a little bit of an aurora here. Not sure about that. And here's a spectrum of a gas giant exoplanet. Exoplanets means it's a planet that's going around another star. And this happens to have the name WASP 96b. And this is taken through a spectroscope, which is one of the instruments on the Webb telescope. And you can see this is again in the infrared. This 0.75 microns is almost into the visible part of the spectrum. Red is right here, just up pretty much on the edge here. And then into the longer wavelengths, 1 micron, which is 10,000 angstroms. I don't know whether you deal with angstroms, but 10,000 angstroms, 20,000 angstroms, 1 micron, 2 microns. And you can see the lines of water vapor, which are in this gas giant. So we know this gas giant has water in it. Water tends to have a lot of absorption and emission lines in, depending on the temperature, in the infrared. And one of the things that you notice on a warm night, if you go out on a cloudy night and it's pretty humid, you'll notice that it's warmer out because the water acts almost like a greenhouse gas, trapping the energy from the radiating from the Earth and keeping the Earth's atmosphere and warm. Here's another picture from the Milky Way. This is a star that had exploded. In fact, it's a very interesting star. It's a nova, and you can see a couple different pictures of it. Here on the left, you'll see this bright star. And you actually see this, by the way, this little line here is a distant galaxy, which is behind that, way out and much, much farther away than the Milky Way. And on this side, you can see it again, this little line, that's the same galaxy. But here, in this case, you can see it's actually, instead of one star here, there are actually two stars. And this left-hand star is the one that's actually exploding. And you can see these different rings indicating that this star has exploded many times. Each time it explodes, it puffs out part of itself, causing these rings to form, more and more rings around and around. And what happens is, because this other star is so close to it, once a star is in its dying phase, which is a white dwarf star, it can only reach a certain stable mass, about 1.5 times the mass of the sun. And so what's happening, and if it gets larger than that, it will actually explode and throw out that extra mass. And what's happening is this other star, which is a regular star, but it's its companion, is transferring energy because they're so close. Sorry, transferring gas from the one star to the other. And once that other star, the one that's a nova, reaches 1.5 times the mass of the sun, it ejects gas. So this will explode and explode and explode and explode over time. Pretty neat stuff. Okay, this is a picture, one of the great pictures taken fairly early on, in the middle of maybe August or September of last year. And this is a picture of a distant group of galaxies. Now, each one of these is something like the Milky Way. In fact, you can see on the right here, this is a spiral galaxy. So you remember that the picture I showed you of the Milky Way galaxy? This is like the Milky Way galaxy. And this is all within one large supercluster of galaxies. And this big sort of round thing is the central giant elliptical galaxy, which is in the middle of this cluster of galaxies, which has enough gravitational pull to keep all these galaxies together. Now, what's more interesting are these little streaks. And I'll tell you more about what they are a little bit later. That's a teaser for you. But you can see all these, almost everything you see here is a galaxy. There are a few stars. Some of the stars you can see, typically they show themselves as little spikes. By the way, these spikes are not real in the star. This is caused by the refraction of the secondary mirror in the telescope, which has struts that hold it in place. And so those are just diffraction patterns from that mirror. If you have a larger object like a galaxy, it's spread out enough so that it doesn't create those diffraction patterns. They're obscured by the light from the other parts of the galaxy. This is an incredible picture. Think about this. Okay, I'm going to go back a little history for you, and I'm old enough that I can tell you a little bit about this history. Edwin Hubble, who was the namesake for the Hubble telescope, was a great astronomer who worked primarily at Caltech, using the 100-inch Mount Wilson telescope, the Hooker telescope, which is, if you go into Los Angeles, you can actually see Mount Wilson. It's now in a lot of smog, and it isn't used very much anymore. But Hubble was taking spectra of many, many galaxies. And he discovered something which is called the Hubble law, which I'll talk about in a second. He used information, and I'm going to give you a little history lesson here, from a woman named Henrietta Leavitt. Henrietta Leavitt worked as a computer, She was an astronomy computer at Harvard, and she lived from 1868 to 1923. And she was one of a bunch of women who were hired by Harvard to analyze data. And I think it's sort of fun to talk about her a little bit and about some of the other people who she worked with. Harvard would not allow women to use the telescopes directly, so they had to just analyze data. It's interesting, later on when I was an undergraduate, I was a senior in college, we had a first-year graduate student named Sandy Morse, and I was one of two seniors who taught her how to use the big 15-inch telescope at Harvard. And a little did we know that Sandy would go on to become Sandra Faber, who's a university professor at the University of California and one of the most famous observational astronomers in the world. So things changed a lot over the years. Well, what Leavitt found, which was very important, she observed a certain kind of star, which was called a type 1 Cepheid variable. The prototype of that star is found in the constellation Cephus, so it's called a Cepheid. And what she found was that she observed these stars in one of the two neighboring galaxies to us, which are called the Large and Small Magellanic Clouds. They're small satellite galaxies to the Milky Way, and that she could observe them on a regular basis, getting brighter and then fainter. And for example, a star would take 3 days to go from bright to faint. Then other stars would take 10 days, and other stars here all the way up to 100 days, you can see. And what she found in a very tight correlation was the longer it takes, the brighter the star is. And so if you can find a star that is a Cepheid variable in a distant galaxy where you don't know the distance, you can measure its period changing from faint to bright to faint again. And by looking at its period, you can tell how bright it really is. And by seeing how bright it really is compared to how bright it appears to be, you can determine the distance to that galaxy. And that happens to be an incredibly important tool to determine how far galaxies are. Well, Harvard hired a lot of these women. Here's a picture of a bunch of them in 1925. And I want to point out, by that time, Leavitt had passed away, but there were a famous one right here in the middle is Annie Cannon, who's also very famous for her work on stars. And above here is a very famous woman, Cecilia Payne, who later married Sergei Gaposchkin, became Cecilia Payne Gaposchkin. Cecilia Payne was hired as a computer, and she continued to go to school, though, at Harvard, which most of these people did not. And she ended up getting the very first PhD for a woman at Harvard University. And then later on, she became the first woman full professor at Harvard. And I was able to get to meet her and work with her, and it was very interesting. She was toward the end of her career, and I took her very last class that she taught on variable stars. And I'll show you another picture of her in a minute. And here she is a little bit by herself. By the time I knew her, this was in the late 60s, so about 12, 13 years before she passed away. And Cecilia was a very interesting woman. She's very tall. She was maybe almost 6 feet. She was maybe 5'10". And when I took her class, which was although I was an undergraduate, it was a graduate class, and she ordered the 4 graduate students around, and she chain smoked. It was the very first person I ever saw that chain smoked, and she smoked usually had 2 cigarettes going at the same time. and she would switch between one, lighting up one with the ending of the other one. And she did this all through class. And at one point she had 3 cigarettes going. But she studied Cepheid variables as one of the things she studied. I happened to work with Frances Wright, who was about her age, who had started out as a secretary in the Harvard Observatory, although she had a master's degree from Brown. And then later on, she ended up getting her PhD. And she also studied Cepheid variables. And I actually measured Cepheid variables the summer of my junior year, working for Frances, and measured the periods of Cepheid variable stars. And Cecilia's husband was working in the same room with me. He had an assistant, and so he was much faster than I was in measuring the periods of Cepheid variables. But Frances and Cecilia both worked on Cepheid variable stars, and I got the chance to do that also. Well, Hubble took the information that Henrietta Leavitt's law told him and was able to figure out that here are galaxies. These are each point here is a galaxy. And what he found out by measuring the distance, since he knew the distance to the galaxy because they had Cepheid variables in them, he also found out that the galaxies that were farther away were galaxies that were actually moving faster away from us. And this is known as the Hubble law. How he measured the speed of the galaxies was very simple. It was through the Doppler effect. And here's the meaning of the Hubble law. The greater the recessional velocity, that is how fast they're going away from us, the greater the distance. The redshift, or the shift of the color toward longer wavelengths, measures the velocity. And you've seen this with, if you've ever seen the Doppler effect for sound, you can hear an ambulance siren. If it's coming toward you, the pitch, it gets louder, but also the pitch increases, higher frequency. And if it goes away from you, it goes to lower frequency. And you can hear that when the ambulance comes toward you, and then suddenly, if it passes you, and then the frequency drops. And this also works with a radar gun. So if the policeman is capturing your speed with a radar gun, or you go to a baseball game and you're measuring the speed of a pitch, you're using the same principle with light, with the electromagnetic spectrum. Well, this was incredibly important, that if you go further and further away, you could see the telescopes, you could see that the galaxies are moving faster and faster. And that came to pass that this was developed into the idea that the universe is expanding. And we now know that the universe is expanding, and because of the shape of the curve, which is basically a straight line, that the universe is expanding in such a way that if you reverse time, all the galaxies would come together at one point. And it was about 13.6 billion years ago that all the galaxies in the whole universe were together in a very tight bunch. And then something happened. We called it the Big Bang, and the galaxies started flying apart. Here are 4 galaxies, actually 5 galaxies, quintet, 1, 2, 3, 4, and 5 up here, that look like they're all, gravitationally attracted to each other. And it turns out that 4 of them, 1, 2, 3, 4, are, but this one happens to have a much smaller redshift, and it's actually much closer to us. So that is a sort of a deceptive picture, because it looks like they're all bunched together, but it's actually these 4 that are bunched together, and this one isn't. This is again a picture from the Webb telescope. Here's another one. Here's another galaxy. This is called a cartwheel galaxy. This has, again, has a regular spiral, and you can see the spiral arms coming out this way, and then it has a ring. These rings typically are areas of star formation where there is a lot of hot gas, and there are often collisions that occur and stars are forming. And here's another couple of galaxies in the background. And you can see all these little things. Almost all of these are galaxies. You can see the spiral galaxy here. And again, another picture from the Webb telescope. Now, I'm going to finish up with a picture. It's called an Einstein ring. This is taken by the Webb telescope. This is a galaxy in the middle, that little blue dot, and around it is a circle. And if you take the spectrum of this circle, you will find out that all these different points have exactly the same spectrum. What does that mean? Well, this is what Einstein predicted. He said, look, if you've got some galaxies here, especially a big one, and you have a very distant galaxy, then what Einstein predicted from his theory of relativity was that light will be bent by sufficient mass. And this light is being bent and then comes to the Earth. And the light from galaxy going around the bottom of this cluster of galaxies will also be bent. And these will also be bent. And what you will see, if you're lucky, will be a ring around one of these galaxies that is the light from this distant galaxy. So what you're seeing is actually a galaxy behind a galaxy, but the light, because of Einstein's theory, has been bent around this central galaxy in the middle here. And that's called a gravitational lens. And Einstein predicted this. It was not observed for many, many years. He was way ahead of his time. Actually, when he came up with his special theory of relativity, I think that was a couple years before the Wright brothers sent up their first airplane. So this was way before we had satellites and space telescopes. And so finally, this picture, which is the picture I showed you earlier. And what are these little arcs? And you notice most of these arcs are around this central galaxy. This is some distant galaxy, or maybe a few distant galaxies, whose lights are being bent by the gravitational pull of this central galaxy. So all these little arcs are examples of parts of Einstein rings of very, very distant galaxies, which are beyond this cluster of galaxy. And right now, we are able to observe the farthest galaxies that we've ever observed. I think it's getting close to 12 billion light years from here, 11 plus billion light years from here, and very close to within a 10% or so, 15% of the very beginning of the universe, certainly of our universe. Okay, well, that's a little bit about the Webb telescope, a little history of astronomy from the perspective of women in astronomy, and hope you enjoyed it.
Oh, yeah.
Okay, so if you have any questions, I'd be happy to answer them or try.
If you have a question, please go to the microphone. We can hear you.
Are there any questions in chat too?
No.
Okay, I'm gonna close. Oh yeah, I see a chat, one chat. Let me see. Oh, this is welcome. Okay, this is early. All right, go ahead.
If you are close to seeing what the end of the galaxy look like, I mean, what would you expect to see? I mean, how would you be able to tell that you're at the end of the what you can see in the solar system, in the galaxy?
And in the universe, really.
Yes.
When you're looking farther and farther away, the one thing that we do that geologists do in a different way is that as you look into the layers of the Earth, you're looking backwards in time. What we're doing is looking backwards in time as we look further and further away from the Earth. So if you're looking at the sun, you're looking 8 minutes. The sun is about 8 light minutes from here. So you're not seeing the sun as it is right now, but you're seeing the sun as it was 8 minutes ago. And you can go further and further away. If you're looking at Pluto, it's a few days away. And if you're looking at the Andromeda Galaxy, it's a few million years ago. And if you're looking at these very distant objects, they can be as they were 10 or 11 billion years ago. So you're seeing the galaxies there during their initial phases of life. So the stars that you see or the objects you see within the galaxies, the kinds of spectrum are representing what they were like. And in fact, many of the objects that you might see that are very, very bright have already burnt out and no longer exist. So this is giving us a clue, first of all, to what the makeup of those galaxies was in the early days, and probably what the Milky Way was like 11 billion years ago, since we can only see the Milky Way as it is now, or at least within a few tens of, maybe a few 100,000 years of its life. Astronomers deal with really long lifetimes, so we don't worry about something that happened 10 years ago. We worry about things that happened millions of years ago. I hope that explains it. Okay, any other questions you might have?
Noel, can you go ahead and vocalize that question so that the room can hear?
Oh,
It's actually Roger. Hi. My question was, what's next for Webb? I keep looking for new pictures, and there's no sort of schedule of what's coming up. You know, I just have to keep looking to see what they must have a plan. You know, for space missions, they've got things planned out for months, years. So,
yes.
So what can we look forward to?
Right. Well, one of the things that when there were a consortium of organizations that funded the Webb Telescope, and they get dibs on observing time, so they get the better choices. But other parts of the time are open to people in competition. So you can apply for time to observe on different instruments on the telescope. And so there are people with their sort of general overall mission, what you can observe, but it's pretty broad for the Webb telescope. And I deliberately showed you some pictures of the planets, which are close. So there are things that are in our solar system. There is material within our galaxy, like the nova that you saw, and some of like the Tarantula Nebula and things like that. That's within the Milky Way. And then you've got the things that are more distant galaxies, and then things that stretch all the way out to the very distant past. So we're looking at a whole bunch of things. And I'll tell you the thing that, well, I was in school in the 60s and 70s. And at that time, we thought we knew pretty much everything, not in great detail, but we were pretty confident as astronomers. It turned out to be falsely confident that we knew just about, well, we know pretty much about the universe. There's some little details that we don't know, but we'll figure those out over time. And then two big things happened. We discovered that about 3/4 of the first we discovered about 3/4 of the universe that we thought we knew. We didn't know. There was called dark matter. And that was the first big, so we thought, okay, well, we thought we knew 95 so plus percent. Now we're down to 25% that we know. There's this 75%, it's called dark matter. What is it? It's dark matter. What is it? We don't know. It's except that we can't see it, but we can feel its gravity. We can see the effect it has on objects, but we don't know what it is. Then later on, not too much later, there was a great observational feat measuring this expansion of the universe. And of course, the universe, because of gravity, has to be slowing down. And the question was, how much is it going to slow down? Is it going to stop and then come back on itself, or is it going to continue on forever? And to everyone's surprise, and that means everyone's surprise, the universe is actually accelerating in its expansion, which goes against what we know about gravity. So there must be another force that's going on that. And so and by the way, one of our local folks, Sal Perlmutter, won the Nobel Prize for that. Well, he led one of the two teams that discovered this. And he's at Cal at UC Berkeley. And what do we call that? We call it dark energy. And it turns out dark energy is most of the mass energy of the universe. So now we're down to about 5% is stuff we know. What I thought when I was in school was everything is now about 5%. About 70+% is dark energy, and about 20-some% is dark matter. So where are we in astronomy? Way back before when I was started school. We don't know. It's all stuff. So this is a very exciting time to be an astronomer because it's all new and all different. It's like you folks thought, okay, the universe, well, it's like, I think probably when Lord Kelvin figured out how old the Earth was, figuring out, and he was completely wrong by a factor of 1,000 or more, right? He thought it was 1 million some years old, and you guys all figured out it was 5 billion years old, or 4 billion years old. And that's where we are right now in this stage, except we don't know what these two things are. It's called dark because we don't have explanation. We could say unknown matter, unknown energy, but they just call it dark because you can't see it, can't detect it. So those are big puzzles that the James Webb Telescope is looking for, but there's no guarantee that it will find that. It was designed to explore really distant. It's almost like the Star Trek, whatever, to explore galaxies and things like that. Okay. Any other questions that people have? Happy to answer. Try to answer. Okay, somebody's.
Yes. Two-part question. What's the power source for the rockets that keep the Webb in its constant orbit? And how long is the projected life expectancy?
Yeah, I mentioned a little bit before. They're basically they're gas powered. There's it's mechanical rockets, and they were hoping initially that there was enough propellant in it to go 10 years, and because the orbit was so well done and they didn't have to use any extra energy, it looks like it's going to be closer to 30 years. So that was a real bonus. The power, that's the power to keep it in position, and there has to be sometimes to move it a little bit here and there. The power that runs the electronics and so forth is mostly the solar array, and that's capturing solar energy, but that's not nearly enough to move a telescope around. it's a big telescope. I mean, it's, sorry, did I say something? Well, anyway, it's really big. Yeah, go ahead. Any other question?
Yeah, hi, my question is, well, one, it's really cool to see these images of solar system planets. It's also really cool to see data from exoplanets. What
Right.
can you tell me about how the telescope crew, how the team balances planetary work versus, star stuff that geologists aren't so
Interesting.
vitally interested in? How do they balance those
Right.
needs for this one telescope?
Right. That is an interesting question. You actually apply for time, and there's a committee that ranks you and gets you to the time. And so it's based on they do have some priorities. So and some of the, as I was mentioning earlier, the sponsoring institutions automatically get certain amounts of time. So those things are allocated, and some of them have like exoplanets is one of the an investigator's main interest, and that investigator will use that time for the exoplanets. There are a couple different instruments that are being used, and in some cases they can use they can switch back and forth between the instruments. One of the great advantages, and I never observed with a satellite or a space telescope. When I was observing at Lick Observatory, for example, one of the things is you apply for time and you get, let's say you get 3 days or 4 days on the big telescope. There's a 120-inch telescope and 36-inch telescope, and you get a time on that. And if you go up in the mountain and it's cloudy, that's it. You lose your time. You don't, you fly again. So there's it's a little bit potluck. The advantage to unless there's a mechanical problem, it's always clear in space. So when you're going to be observing, you get to observe, and you're going to get the time. So that's so the utilization time is very high, while in the other telescopes, again, the telescopes that are in very high mountains, typically you don't have weather is not as much of a problem. Mount Hamilton is not that high up. You saw some pictures recently. There's snow on Mount Hamilton, which is pretty common. And but if you're at Mauna Kea, which is where there are a bunch of telescopes, or in South America in the Andes, where there are some really good instruments, you can get good guarantee of getting time. Okay, I'll tell you a geology issue. Astronomers typically don't know anything about geology, but as time has gone on, they've learned more, especially when we started studying planets, because you've got people who are astronomers like me. I didn't know anything about solids. I mean, astronomy doesn't deal. So I know about plasmas and gases and all sorts of things, but rocks, those are not something that astronomers know anything about. So when people started going into planetary astronomy, when they were actually getting photographs of the moon, getting photographs of Mars, and so forth, then a whole bunch of new people came in who were and planetary astronomy was really became a big field, and especially with NASA putting a lot of money into things like the Mariner projects and the different other spacecraft sending out in the 60s. Carl Sagan was one of those people. He was an assistant professor at Harvard when I was an undergraduate, and he also did biology. He did a lot of biology, and of course, astronomers didn't do biology. I mean, studying stars, are not nothing alive there, and so it was not a respected field, and he didn't get tenure, by the way. I don't know whether you know that. Carl Sagan was an assistant professor, and he did not get tenure. And the rumor was, at least us undergraduates, was he was already divorced from his first wife, and he was living with his second Linda, his second wife, a person who would become his second wife, and he drove a convertible. And so the staid professors at Harvard also didn't like the fact that there was this young guy who was driving a convertible and had a woman, was living with a woman to whom he was not married. So he went to Cornell. Did pretty well there. Anyway, sorry. Go ahead. Another
Hi.
question?
Yeah, I have a question about the mechanics of kind of pointing the telescope. How much time does it take to aim the telescope and get it right on where you want to? Where's the energy coming from to do that? Or maybe it doesn't take much energy.
Yeah, it doesn't take too much energy, and I don't know the exact slew rates, but normally what you do is, if you've got a program, what you end up doing is, as you're preparing the program, and one of the advantages, of course, being where it is, which is basically the Earth is blocking most of the light of the sun. It's far enough away that there's the Earth cannot block out the entire sun. So there's a little bit of sunlight that's coming. That's why the solar rays work on the side facing the bottom side of this picture. And so the solar energy, there's enough the solar rays provide enough energy. The key there, though, is you set up the program so that you're slewing small distances. So you line up your program to go the minimum distance between each object that you're interested in looking at. And so that takes the minimum amount of energy, also takes the minimum amount of time. It doesn't take that much energy to slew a rock. I'm a telescope. I'm trying to think. I observed we had a 61-inch telescope, which is smaller, but it's heavier than this at Harvard. And you could go in a minute or so between objects fairly easily. It's all computerized. So the telescope moves fairly quickly and very directly to the object. And you don't have to worry about so much about the Earth's rotation. That's a big thing with Earth-based telescopes, because the Earth is turning once every 24 hours. While this one, you can keep it aiming at the same spot without having any motor to turn the telescope. I don't have a direct answer for you. I don't know the exact slew rates, though, for the telescope.
Okay, thanks.
Okay.
Anyone else online have a question? I think that's it. Thank you very much.
Okay. Well, thank you. It was fun, and good luck with your program. I'll sign off now. Thank you.
Very much.
Thank you very
Okay.
much. It was really interesting.
Okay, thank you.